Hello, my name is Luis Serrano, and today I'm going to tell you about Bessel's correction, which is the reason we divide by n minus 1 to estimate the variance instead of dividing by n. So here is the premise. Let's say that you want to find the average height of all human beings in the world. Well, how can you do this? You can go around the world with a measuring tape and measure every single human being and then calculate the average. But that's very hard to do because there's a lot of human beings. So what can you do to get a good estimate? Well, you can pick 10 human beings, for example, at random. It has to be completely random. You can measure their heights and take that average. And that is a good estimate for the average of the height of all human beings. So far, so good. The problem arises when you want to estimate the variance. What is the variance? Well, it is a measure of how much the height varies among human beings. So if we're all the same height, that variance is 0. And if we have vastly different heights, then that variance is high. Now, I'll be more specific in the video, but here's how to calculate variance in a nutshell. You take the average height of human beings, and then you see how far each person deviates from that mean. Take the squares of all those differences and find the average of them. So, again, if I want to calculate the variance of the height of human beings in the world, I can't go around asking everybody for their height. Instead, I take my little set of 10 randomly chosen people and I calculate the variance for them. Now, here's the problem. The estimate of the variance for those 10 people is not a good estimate for the variance of all the people in the world. And one reason for this is that I'm not working with the correct average, but I'll get to that later. Now, here's a small trick they give you to fix this estimate for the variance. Remember that I said that the variance is an average over all these 10 people of some difference? Well, that is not a good estimate. But if you, instead of dividing by 10, you divide by 9, then you get a good estimate. So it's an average over 10 people, but I don't want to divide it by 10. I want to divide it by 9. That's the Bessel correction. They say don't divide by n, divide by n minus 1, and then you have a perfect estimate of the variance of the population. And this works for a distribution. If I want to take the variance of a distribution and estimate it, I take n points and I calculate their variance but divide it by a minus 1 instead of n. Now that has driven me crazy for many years because I don't understand why this n minus 1 is there. And for years I've been looking, I've been reading the literature, I've been writing many things, trying many examples, asking everyone that I can, and it still hasn't been clear because in the books and in the articles, they always have a very strict mathematical explanation that shows where the n minus 1 appears, but it doesn't really make it intuitive or graphical. I need somewhere where I have n things and I delete one of them and I have n minus 1 and that's where I divide. So I'm happy to say that after many years of trying and talking to many people, I finally have a good explanation for this Bessel correction, for this n minus 1 in the denominator. And here's the interesting thing. To understand this n minus 1, we actually have to look at a different definition of variance. So I'm going to show you a different way of defining variance. This new definition of variance actually doesn't use the mean. And I haven't seen it anywhere in the literature. It may or may not be new. If you've seen it somewhere, please put it in the comments because I'm very curious. So anyway, let's get to it. Here is the story of Bessel correction and how to correctly estimate variance. So first, let's recap mean and variance very quickly. Let's say you have a probability distribution and the mean is the place where you would balance it as a weight. The mean is also the average of all the values that we sampled from this distribution. There's infinitely many, but you can still think of an average. Now, in order to estimate the mean, we can simply sample some points in the distribution and then take the average of these points. That would be the place where these points get balanced. So let's look at an example. What you would do is put some numbers here. So let's put a 0 somewhere here and it can go anywhere. And based on this 0, what are these values? Let's say they're 1, 2, 5, and 8. What's the average of 1, 2, 5, and 8? Well, it's 4. So 4 is going to be the mean or the average, and that's where we can balance those 4 points. Now, here is another set of 4 points, and their average is the average of 2, 3, 5, and 6, which is also 4. And the formula for the average is this one over here. It's 1 over n, the number of points, summation of xi, where xi are the values. And the summation goes from 1 to n. Now that's for the mean, However, there's another measure, which is the variance. It tells you if points are spread apart from the center or if they're close to the center. And that measure is the variance. Distributions can look very different. Some are wide and some are narrow. And the ones that are wide will have a large variance, and the ones that are narrow will have a small variance. The way to denote the variance is var. Now, if we're thinking of a set, not a distribution, how do we calculate the variance? Well, first we take the mean, and then we want to see how spread apart the points are. Then we simply take the distances from the points to the mean. And we're going to calculate the average of these 4 points. But there's a small problem. If I take the difference between a point and the mean, when the point's at the right, I get a positive number. And if it's at the left, I get a negative number. And I don't want these numbers to cancel out, because if they're both big, I actually want them to add up. So how do I turn this -3 into a positive number? Well, I can just square every single one of these differences. And now I get them all positive. So that's what we're going to do. We're going to take the squares of the distances from the center to the points, and we're going to average these squares. So we're going to take their sum and divide it by 4 in this case, because there's 4 points. So let's look at the two distributions, and remember that the formula for the average is this one over here, which means that they both have an average of 4. And now, on the one on the left, we're going to have these 4 squares, and on top you can see the calculation, 1 minus 4 squared plus 2 minus 4 squared, etc., divided by 4. And that's the average of 9, 4, 1, and 6, which is 7.5. So the distribution on the left has a variance of 7.5. If we do the same thing on the right, then we get 2 minus 4 squared plus 3 minus 4 squared, etc., divided by 4. You can see this is much smaller because the squares are smaller because the points are closer to the center. That's the average of 4, 1, 1, and 4, which is 2.5. So the one on the left has a large variance of 7.5 because the points are spread out. And the one on the right has a small variance of 2.5 because the points are much closer to the center. So that's the variance in a nutshell. Now, as I mentioned before, when you have a distribution, something you want to do is estimate the mean. Instead of taking the average of all the points, you just sample some points. So you pick some random points here, and then you take the average of these points. So let's say the average of these points is over here. That's the sample mean. Now, that doesn't need to be the same real mean, because it depends on which points we sampled. However, it's a pretty good estimate of it, which means that if we do it randomly, we're very likely to get something really close to the real mean. And the more points that we sample, the more likely that we're going to get something really close to the real mean of the distribution. Unfortunately, the same thing doesn't happen for the variance. So here's the problem. If we're going to estimate the variance of this distribution based on the variance of the sample of 4 points that we took, then we have to, first of all, take the real mean of the distribution. This is not the mean of the 4 points. This is the mean of the whole distribution. And then take the distances from that mean to the points and then square them and take their average. Now, this is a good estimate. If we were able to do this, we would be calculating the correct mean. However, it's too much to ask because we don't have information of mu, the real mean. In order to know the mean, we need to know the average of all the points in the distribution, and we only have these 4 points. The best we can do is find the sample mean, so the mean of these 4 points, and then calculate the variance with respect to those 4 points, giving us this formula. However, this is a bad estimate because we didn't use the correct mean. So how do we fix this? Well, we can't go and calculate the original mean. That's too much work. So what we're going to do is the following trick. The trick is, instead of taking 1 over n, change that to 1 over n minus 1, and that gives you a good estimate for some reason. That is called Bessel's correction. In other words, Bessel's correction says, this is not the correct estimate, forget about this n, and instead take n minus 1 as the denominator. So there are 2 questions. The first one is, what do we mean by better estimate? And I'll elaborate this in a minute. But the main question I have is, why, oh why, is this n minus 1? Why do we divide by n minus 1 instead of n? So I've seen 2 explanations. One is the standard mathematical derivation, which if you look there, there's an n minus 1 appearing, but that gives very little insight. And the other one is an explanation that I get from experts a lot, and I don't fully understand it, to be honest. It says the following. Notice that if I take some points, the average of these points is something that I already know. So that gives me n minus 1 degrees of freedom because I pick n minus 1 points. The last one is already picked to match the average. So therefore, I should divide by n minus 1 instead of n. And they may know something I don't know, because when I look at this explanation, I can't make sense of it. In particular, this part over here, if there's n minus 1 degrees of freedom, then you divide by n minus 1 instead of n. So if you understand this, please put it in the comments and help me out, because I still haven't been able to. And so here's what I want. This is the formula for the variance. I want there to be n things somewhere and one of them to be special, and therefore I only have to count n minus 1, and because of this n minus 1, that I divide by n minus 1 instead of n. So that's where we're getting in this video. But before, I'm going to tell you what exactly do we mean by better estimate. Why is that original estimate bad, and why do we need a better one? So before we get to the n minus 1, let me tell you what the problem is with the estimation. So estimating the mean is very simple. Let's say that we have these 4 points and we want to estimate the mean. So that's easy. It's 4 because the average of 1, 2, 5, and 8 is 4. However, let's say that 4 numbers is too much. I don't want to make that many calculations, and I want to maybe not get the best value, but I want to make less calculations. So I'm going to pick 2 random points. I'm going to pick the 1 and I'm going to pick the 8. And then I'm going to take the average of these 2 points. I'm going to call it m, and that's the average of 1 and 8, which is 4.5. Now 4.5 is not as good as 4. It's an estimate, but I had to do less operations, so I'll take it. And the question is this a good estimate? Well, the answer is yes, but let me tell you what I mean by is this a good estimate. So let's say that we take 2 random points. How many ways can we take 2 random points? Well, it's in 6 ways. We can take the 1, 2, 1, 5, 1, 8, 2, 5, 2, 8, and 5, 8. And each one gives us a different estimate for the average of the 4 points. And the values range. It can be 1.5, 3, 4.5, 3.5, 5, and 6.5. All of these are estimates of the 4. So if I take 2 random points, then I could land into any of these 6 values for the estimate of that average, which is 4. So here's an important property that these estimates have to have. When I take the average of all of them, it has to be 4. Because if I'm taking a random 2 points, then I'm taking a random number as my estimate of 4, and the average of all these should be 4. And in this case, it is. So it is the correct estimate. So I may be completely off if I take 2 points that are not very good. But at the end of the day, if I pick 2 random points on average, my average will be 4. So that's an important property that estimates have to have. However, unfortunately, this doesn't happen for variance, and let me show you very quickly. Again, we have our 4 points, and we have our average, which is 4, and the variance is this number over here, the average of 1 minus 4 squared, 2 minus 4 squared, 5 minus 4 squared, and 8 minus 4 squared, which is the average of these 4 numbers, and as we saw before, is 7.5. Now I'm going to take 2 random points, again, the 1 and the 8, and we're going to calculate the variance of these 2. However, I can't calculate it with mu equals 4 as the average because I don't know this. If I only have 2 points, I don't know the average of the original 4 points, because the point is that I don't want to make 4 calculations, I want to make 2. So I don't know that 4. Therefore, I have to pick what I got, which is the average of the 2 points that I have. The average of my sample, which is m, equals 4.5, the average of 1 and 8. And now the estimate of the variance with this mean m is the average of 1 minus 4.5 squared and 8 minus 4.5 squared, which is the average of these 2 numbers, which is 12.25. And now the point is that this is not the correct estimate for the 7.5. And the reason is because I didn't do it with the correct mean. And let me show you what I mean by this is an incorrect estimate. If we take the 6 possibilities for all the choices of 2 points among this set of 4 points, well, if I knew the average was 4, I would get the correct estimate for the variance. But I don't know this. I have to figure out the average for each one of these sets of 2 points. That gives me the incorrect estimate. And let's actually calculate it. So if I calculate the variance of each set of 2 points based on that sample mean, then I get these values. 0.25, 4, 12.25, 2.25, 9, and 2.25. And when I average them out, I don't get the 7.5, which is the original variance of the 4 points. I get 5 instead of 7.5, so it's an underestimate. It's actually always going to be an underestimate. So what do I do to get the correct estimate? Well, let's look at the formula for variance in the top, and let's change the denominator from n to n minus 1. So what is that? Well, in the calculation of the variance for the 4 points, I changed the 4 to a 3. And when I change the 4 to a 3, this is no longer 7.5, now it's a 10. And what happens with the bottom ones? Well, the denominators are 2 because the sets have 2 points. I change those 2's to 1's. And when I change those 2's to 1's, the values change. They basically get multiplied by 2. And now when I take the average of all these new estimates for the variances, well, I get my 10. So we were not that off in the first estimate. We just had to change the denominator, or in other words, we had to multiply by n over n minus 1 in order to get the correct estimate. So when we go back here, well, the 12.25 was not a good estimate for the 7.5, but if we divide by 3 instead of 4, and we get a 10, and when we change these denominators to for a denominator of 1, then we get a new estimate for the variance, which is 25, and believe it or not, this 25 is a better estimate for the 10 than the 12.25 was an estimate for the 7.5, and it doesn't look like, but as you saw before, when we take all the pairs of points and average the estimates, then we do get 10. So, as we saw before, should not be an n in the denominator, it should be an n minus 1. So now we're getting to the important part, which is why is this the case? Why is it that dividing by n minus 1 gives us the better estimate that averages out to the correct thing? That's what I'm going to tell you next. But before, let me tell you a new way of calculating the variance. So now I'm going to show you a new way to calculate the variance that makes the Bessel correction much more intuitive. So let's review the known method. Let's say you want to calculate the variance of this set of 4 points. So you calculate the mean mu, then you look at all the distances from mu to the points and take the square of that. So you do that for all the 4 points, and then take the average of these squares, divide by 4, and then you get variance of x, where x is this set. Now let's do method 2. That's the new way. So let's say that we don't know mu, or we are not interested in calculating mu. Is there any way we can still tell how spread out this data set is? Well, if we can't take distances to mu, let's take distances from one point to another. So let's say these 2 points over here, and take the square again so we don't get negative numbers. And then let's do this for every pair of points. So here it is for the first 2 points. Here's for the third and the fourth. And then for every single pair, there are 6 ways to pick a pair from a set of 4 points. And then we take the average of these 6 squares, and we're going to call that the variance to differentiate from the variance. We're using a different b. And it makes sense that variance is also a way to tell if a set is spread out or narrow. But what is exactly the relation between variance and variance? Well, they're actually very related. I'm going to tell you very soon. But first, let me convince you that this also works for distributions. So if we're going to calculate the variance here, we take every single point and the square of the distance from it to mu. And if we are able to do this for every point, there's infinitely many, but if we manage to take this average for all the points, we get variance of x. Now what happens in the bottom one? Well, we take 2 random points in every possible way. So we take all the infinite pairs of 2 random points. I know I'm being a bit vague here, but bear with me. And if we manage to take this average, then we get the variance. So now the question is, what is the relation between variance and variance? Well, you will be pleasantly surprised to know that to get the variance from the variance, all you have to do is divide by 2, because variance is twice the variance. And it makes sense that variance measures spread, because if I have a distribution with low variance, points are close to each other, and so these squares are mostly gonna be small. Whereas if I have a high variance distribution, a widespread one like the one on the right, then the points are going to be far away, so these squares are going to be big. Now we've understood the variance, but here's a question. Where does Bessel correction come in? Well, I'm going to show you a bad way to calculate the variance, and then we're going to fix it with something that's equivalent to Bessel correction. Let's calculate the variance here. So we're going to take all the differences, 2 minus 1 squared, then 5 minus 1 squared, then 8 minus 1 squared, and we're going to fit them in this square on the right. Then we have 5 minus 2 squared, 8 minus 2 squared, and finally 8 minus 5 squared. Now, I also want to do them in the other direction. So not just 2 minus 1, but also 1 minus 2 squared, 1 minus 5, and you get where this is going. So we're going to fill this square over here at the left. But now the square on the left is missing a diagonal. Where should it go? Well, we've taken pairs of points. What if we take pairs of equal points? So 1 minus 1 squared, that's a 0. Then 2 minus 2 squared. Then 5 minus 5 squared. And then 8 minus 8 squared. And I claim that this is a bad way to calculate it, and then I'm going to fix it. But let's calculate it. Well, all the numbers are now calculated in this table in the right, 0, 1, 16, 49, etc. What's the formula for the average of the numbers on the left? Well, in this case, n is 4 because we have 4 points, and it's 1 over n times the summation of xi minus xj squared for all pairs of points I and j. Now I'm going to write this here on the right, but let's analyze this more. So first we have this diagonal full of zeros, and then we have a bunch of numbers that are the same here and here because a number squared is equal to its negative squared. But let's look at the red diagonal. Why is that diagonal there? Do we really need to add a bunch of zeros? Those numbers are always gonna be 0. We actually don't need them. So let me remove them. And now we're taking an average not over 16 numbers, but over 12 numbers. In general, what we did is we removed n numbers because there are n diagonals, and therefore we don't divide by n squared, we divide by n squared minus n. And notice that now we don't take the sum over all ij, over all pairs of points. Instead, we take the sum over pairs of different points. Now here we get the exact same sum because we just removed some zeros. Another way to see this is if we rearrange this square to remove this diagonal, then now we don't have a square, we have a rectangle of width n minus 1 and height n. So therefore its area is n times n minus 1, which is a way to factor n squared minus n. So we modified this average. We're no longer divided by n squared, we're dividing by n times n minus 1, and we claim that at the right we have a better estimate because we don't have a bunch of unnecessary zeros. Now notice what we did. We changed an n to an n minus 1. That is exactly Bessel's correction term. So as you can see, it's hard to see why you have to divide by n minus 1 in the original formula for variance. But in this formula for variance, it's very intuitive. We divide by n minus 1 instead of n because we don't want to add all these zeros in our average. We're not taking an average of n squared numbers, we're taking an average of n times n minus 1 numbers. Now an alternate way of doing is noticing that the top right triangle has the exact same numbers as the bottom left triangle, so we can just put them together, and instead of taking the sum over I different than j, we're going to take the sum over I less than j. And we're dividing by n times n minus 1 over 2. And that's the same as n choose 2. If you've seen n choose 2 is the number of ways of picking 2 points out of n that are not ordered. So this is why we're taking them I less than j, because the pair ij and the pair ji count for the exact same pair. So now, just to be super clear, this calculation of variance that we had using different points is not twice the calculation of variance. So from the formula in the bottom, you don't get the formula in the top by dividing by 2. Instead, we take the formula on the bottom and look at all pairs of points. So how are all pairs of points? Well, we can take all the pairs of distinct points and all the pairs of equal points. For the pairs of distinct points, we have to count everything twice. From when we take the point on the left minus the point on the right, from when we take the point on the right minus the point on the left, and then we have 4 zeros for the pairs of equal points, because for each point, we take that point twice as a pair. So when we take the average, we divide by 16 because there are 16 summands in the numerator. When we divide that by 2, we get the formula on top. So here is where Bessel's correction comes in. In the bottom, it's silly to take pairs of equal points because they only add a 0. Something that's always a 0 is predictable. We don't need that value, so we remove it. And when we remove it, we're not dividing by 16 because there's no longer 16 things on the numerator. We're dividing by 12. Now, when we fix the formula on the bottom, we also need to fix the one on the top because we need to change this 4 by a 3, because at the end of the day, when we change a 16 by a 12, we multiplied everything by 4 over 3. That's why we changed the 4 to a 3 on the top. So in summary, removing the zeros that come from picking pairs of equal points is equivalent to changing the n by an n-1, which is Bessel correction in the original calculation for variance. So here's a summary of what we did. We have a bad estimate and we have a good estimate. For method 1, the variance using the mean, our formula is this one over here for the variance. This is without Bessel correction. And the corrected formula is this one with Bessel correction. Now, what happens with the variance? Well, if we're no longer using the mean, but we're using distances between points, then here's the formula for the variance taking any pair of points. Could be the same or could be different. And we corrected that by taking the average over different points, over pairs of different points, and that changed the n to an n-1. So in other words, taking pairs of distinct points is equivalent to using Bessel's correction. And since the formulas on the bottom row give us the formulas on the top row by only dividing by 2, then we can see that taking pairs of distinct points is equivalent to Bessel's correction. Now there's one thing I have not told you yet. See, I mentioned that removing the zeros was good, but I didn't say why. So next, I'm going to tell you why we need to remove those zeros to get a better estimate. Let's say that I want to estimate the variance of this distribution. So I'm going to pick 9 random points, and now I'm going to calculate all their distances squared, including the zeros in the diagonal, which are xi minus xi squared. I have 81 numbers, so this average is 1 over 81 times the sum over all pairs ij of xi minus xj squared. Now let's say that even this is too much. This is too big an average. I don't want to calculate 81 things and then take an average of so many numbers. So I'm going to estimate this estimate, and what I'm going to do is I'm going to pick less than 9 numbers. I'm going to pick 4 out of these 9 numbers, x1 all the way to x4. That means that my square is now going to be smaller. It's only going to have these rows and these columns, which means that my estimate for the estimate of the variance, so my estimate for the variance of 9 points is the variance of these 4 points, which is now 1 over 16, which is 4 squared, summation over all pairs ij of xi minus xj squared, except that now I and j are between 1 and 4. And my hope is that the average on top is an estimate for the average on the bottom. Now, the problem is that this is a bad estimate. And why is this a bad estimate? Well, because on top I have a lot more zeros than on the bottom in proportion. So on top I have 4 zeros out of 16 numbers, so a quarter of them are 0. And on the bottom I have 9 zeros out of 81 numbers, so 1/9 of them are zeros. So the zeros make a lot more noise on the top than they do on the bottom, and they actually decrease my average. So I get a bad estimate. In fact, I get an underestimate. I get less than what I should be getting. And how do we fix this bad estimate? Well, if I were to remove those zeros on top and remove those zeros in the bottom, now my denominator here is no longer 16, it's 12, which is 4 times 3. And in the bottom is 72, no longer 81, because it's 9 times 8, and I've turned my bad estimate into a good estimate. Now, if you don't like the full square with a diagonal and instead you like just a triangle, it's the same thing. My variance here is 1 over 36 times the sum over, now I have 1 less than j of xi minus xj squared, and I want to estimate this by only taking points 1 to 4. So I have these rows and these columns, and a much smaller triangle. Now the variance is 1 over 6, sum of I less than j of xi minus xj squared, for a smaller set of I and j. Now they're in between 1 and 4. And small note, this 6 is 4 times 3 over 2, which is 4 choose 2, the number of ways of picking 2 numbers out of 4. And this 36 is 9 choose 2, or 9 times 8 over 2. And now I claim that the average of the numbers in the top triangle is a good estimate for the average of the numbers in the bottom triangle. And why is it a good estimate? Well, think about this. In the bottom, I have 36 numbers and I'm taking the average. And if I don't want to take an average of 36 numbers, I can simply take a subset of them of 6 numbers, this one over here, and that's the triangle on the top. So I'm estimating an average of 36 numbers by picking 6 random ones and taking the average of those. That is an honest estimate because I don't have those zeros distracting me. Now, what happens when n is really big? When n is really big, then these two numbers are very similar. So if you are taking a huge number of points in your distribution, it doesn't really matter if you use Bessel's correction or not, whether on the variance or on the variance. So at the end of the day, this estimate only makes a big difference if n is small. If n is really large, then you're still doing well with or without Bessel's correction. But if you have 10 points or 5 points or something like that, then you really need to use Bessel's correction to get a better estimate. Now I promised to show you mathematically that variance is equal to 2 times variance, so I have two proofs. The first one is a little slicker and it uses some knowledge about calculating mean and variance. If you're not so familiarized with calculations of expected value and variance, then skip forward to the next one, which is more algebraic. So first, how do we calculate the variance? Well, that is the expected value of x minus y squared, where x is the same distribution as y. In other words, if I want to take differences, I may as well just copy my distribution x into another distribution y and then take their differences. That means I'm taking a random point in x, a random point in y, squaring them, and taking the expected value of that. Now that is exactly the definition of variance of x minus y. Why? Because the expected value of x minus y is 0, because as I said, x is equal to y. So therefore, expected value of x minus y squared is equal to variance of x minus y. Now, by linearity, this is the same as the variance of x plus the variance of y. And the reason is because x and y are independent. When variables are independent, then the variance of their difference is the sum of the variances. And because x is equal to y, then this is the same as 2 times variance of x. And so again, that's the proof if you are familiarized with these calculations, but if not, here's another proof. First, assume that mu equals 0. We can always assume that mu equals 0 because if not, we can always move the distribution and center it and it will still have the same variance and the same variance. So let's calculate this summation of xi minus xj squared for I less than j. Well, if I expand that square, I get this. Xi minus xj squared becomes xi squared plus xj squared minus 2xi xj. Now let's group all those xi squared and xj squared. How many times does each one appear? Well, any xi appears with all the other xj's that are different. So this is going to be n minus 1 times the sum of I equals 1 to n of xi squared. And for the 2xi xj, well, each pair appears exactly once, so I'm going to have minus 2 times summation of I less than j of xi xj. Now, before we go to the next step, let's analyze what this is. Well, remember that mu equals 0. That means that the sum of the variables is 0, because mu is the average of them. If the average of a bunch of numbers is 0, then I multiply by n and I get that the sum is equal to 0. I can square this and I still get 0. And when I square this, I get this, sum of squares plus 2 times the sum of double products. If I pass this to the right, I get that the sum of squares is equal to negative 2 times the sum of the double products. And that is precisely this. So I'm going to change that negative 2 sum of double products to the sum of squares, which in addition to the n minus 1 sum of squares at the left, I have n times the sum of squares. So I have that the sum over I less than j of xi minus xj squared is equal to n times the sum of squares of the xi's. And if I divide both sides by 1 over n squared, I get this over here. That looks familiar because on the right, we get the variance. Now I don't have the Bessel correction term. Don't worry about the Bessel correction term here. But now let's look at the actual definition of the variance, which was this one over here. Now these two are not the same. I need a factor of 1/2. And why is the factor of 1/2? Because the sum on the right is over pairs I less than j, and the sum in the left is over pairs I different than j. So each pair appears twice in the right. For example, x1 minus x2 appears 2 times on the left because I have x1 minus x2 squared and x2 minus x1 squared, and in the right it only appears 1, so I need to divide by 2. And that's why 1/2 times the variance is equal to the variance, or equivalently, variance is equal to 2 times variance. Now here is a question. And now I have the variance and variance again with the Bessel correction. It doesn't really matter if we have the Bessel correction or not. But here is a question. If the variance seems like a more intuitive way of calculating the spread of a distribution or of a data set, at least in terms of the Bessel correction, then why don't we just ditch the variance and start using variance all the time? Well, one reason is complexity. If we want to calculate the variance, how many operations do we need to do? Well, we need to add over all pairs of I and j. that is n square of them, or at least order of n square operations. Now, if we want to calculate the variance, what do? Well, first we need to calculate the mean, and then once we've calculated the mean, then we need to calculate this average over here. Now, that's big O of n operations. Why? Well, it's big O of n to calculate the mean, and then once we're done calculating the mean, then it's another big O of n, but here we add them. So it is actually much faster to estimate the variance than to estimate the variance. So that's a reason why we don't have to ditch the variance, we can still use it. But now we have two things we can use. Sometimes we may need to use the variance, and sometimes we may need to use the variance. And we can just use whichever one is more useful for whatever we're doing. Well, as I mentioned, I wouldn't have been able to make this video or to figure out the variance without the help of my friends. I talked to many people about this throughout the years, and so many people gave me ideas here and there, but the ones who helped the most are Maggie Bosa. She was one of the teachers that I taught the Math for ML specialization at Coursera, and very, very knowledgeable about stats. Also my friend Emerson Leon, a mathematician and data scientist whom I actually know from my years back in the Math Olympiads many years ago. He figured out some really nice geometric arguments for the variance and the variance. And my very own PhD advisor, Sergey Fomin, also gave me some great insights. In particular, he was the one who came up with the clever mathematical argument to prove that variance is equal to 2 times variance. And I want to acknowledge this channel. Stats and Science is a very underrated channel. He has some really nice arguments in a video called Variance yn minus 1. So I highly recommend this channel. I hope it grows. It only has 3 videos, so definitely has potential to be a huge resource for machine learning. So definitely go check it out. And so that's all, folks. As usual, if you enjoyed this video, please hit like, please share it amongst your friends, and subscribe. And feel free to throw in a comment if you have any questions, any comments, or any suggestions for future videos. If you'd like to tweet at me, it's serrano.academy. If you'd like to check out my page where I have a lot of videos, blog posts, and information about courses, etc., check out serrano.academy. And finally, if you'd like to learn more and delve more into these topics, I have a book called Grokking Machine Learning. Here's a discount code, SerranoYT, that is written in the comments as well for 40% discount. So thank you very much for your attention, and see you in the next video.